Today we'll talk about how to evaluate and select classification models. We'll explore evaluation metrics, beyond just accuracy, and different validation methods like cross-validation and bootstrap. We'll also see how to compare models using confidence intervals, ROC curves, and cost-benefit analysis. One of the most important tools in classification evaluation is the confusion matrix. For a binary classification problem, the matrix displays how many true positives, true negatives, false positives, and false negatives there are. These values help derive more specific metrics beyond accuracy, like sensitivity and specificity. Accuracy measures the overall percentage of correctly classified tuples. Error rate is simply 1 minus accuracy. But in class-imbalanced problems, like fraud detection, accuracy alone is misleading. That's where sensitivity, true positive rate, and specificity, true negative rate, become essential. Precision measures how many of the predicted positives are actually correct. Recall, or sensitivity, measures how many actual positives were correctly identified. F1 score is the harmonic mean of precision and recall. For imbalanced data, we might use F-beta to weigh recall more heavily if needed. Here's an example where the model predicted 230 positives, but only 90 were correct, giving a precision of about 39%. Out of 300 actual positive cases, it only got 90, so recall is 30%. Specificity is very high, nearly 99%, which shows the model performs much better at identifying negatives than positives. Let's now discuss validation methods. The holdout method splits the data into training and test sets. To get more reliable estimates, we use cross-validation, especially 10-fold CV. It repeats training/testing over different splits and averages the result. Stratified CV ensures class distribution remains consistent in each fold. Bootstrap sampling is useful when the dataset is small. We sample data with replacement to form training sets, and those not selected form the test set. On average, 63.2% of the original data appears in each training set. Repeating this multiple times helps estimate model performance reliably. What if we want to compare two classifiers, M1 and M2? Their performance difference might be due to random chance. So, we use confidence intervals and statistical significance tests to see if one is genuinely better than the other. In hypothesis testing, we assume a null hypothesis, that there's no difference between M1 and M2. We use 10-fold cross-validation, calculate mean error rates, and apply the t-test to check if the observed difference is statistically significant. There are two versions of the t-test. If the same test set is used for both models, we use a paired t-test. Otherwise, we use a non-paired t-test. Both help determine if the mean difference in error rates is significant beyond random variation. This table shows critical values from the t-distribution for different significance levels and degrees of freedom. For instance, if we choose a 5% significance level, we look up the corresponding t-value for our sample size and compare it with our computed t-statistic. To finalize our hypothesis test, we calculate the t-statistic and compare it with the critical value from the t-table. If it's beyond the threshold, we reject the null hypothesis and conclude that the difference between models is statistically significant. ROC curves are a powerful tool for comparing classifiers. They plot the true positive rate against the false positive rate. The closer the curve is to the top left corner, the better the model. A curve near the diagonal indicates poor performance. The area under the curve AUC summarizes this visually and numerically. When selecting a model, we must look beyond accuracy. Speed, robustness to noise, scalability, and interpretability are crucial. Depending on the application, we may also consider rule compactness or the ability to handle missing values. Choosing the best model involves balancing all these factors.